in general, we take the pH as 7, but that's not technically. In terms of the pH, yeah, it is neutral. But remember, when we get the formation of salts, the salt itself can be acidic or basic. That is why we have the different indicators. Okay. But don't worry too much about that. We don't go into it in the syllabus. So, at the bottom of page 80 there, they have aluminium hydroxide with hydrochloric acid, forms aluminium chloride and water. And calcium hydroxide with hydrochloric acid forms calcium chloride and water. Okay. Yeah. That's just a normal reaction. And then on the next page, there on page 81, they say nothing happens to the calcium hydroxide when the alkali is added. This is expected because calcium hydroxide is a base and bases do not react with other bases or alkalis. Then in the next paragraph, with aluminium hydroxide, however, there is a reaction. The aluminium hydroxide is behaving like an acid. And what do acids do? They donate protons, okay? And it is reacting with the alkali sodium hydroxide. In the reaction, a salt is formed, as in any neutralization, but in the case, aluminium appears in the anion, not as the cation. Now, we don't go into the chemistry of the aluminate. We've got the product is sodium aluminate. You don't need to know the formula. Just know the definition of an amphoteric oxide. All right, and just very simply, it's something that can act as both a proton donor or a proton acceptor. And they won't go into more detail than that. Okay. You need to know the example. Aluminium hydroxide, for example, is an amphoteric oxide. Oxides of zinc and lead are amphoteric. All right. Yes, if you look in your books, page 81, table 5.3, basic oxides are metals. Acidic oxides are nonmetals. Amphoteric oxides are oxides of zinc, aluminium, and lead, and then neutral oxides, we've had them on the board, nitrogen monoxide, carbon monoxide, and dinitrogen monoxide. Water is also considered a neutral oxide, although the chemistry of water becomes quite complicated, which we don't do. Okay, so you can just ignore it. It's fine as it is. Yes, it is. It is. It doesn't fit any pattern. Yes? All right. No. Actually, they won't ask it like that. But if they do give you the reaction, it's taking the proton, then it's a base. And if it's donating a proton, it's an acid. As an example, I won't give water. I would give the others. Okay. All right. Okay. The next thing that we have to have a look at is at the bottom of page 81, salts. Now, what is a salt? A salt is an ionic crystal compound. Ionic means a non-metal bonded onto a metal. The metal loses its electrons, the non-metal gains the electrons. We have positive ions and negative ions that attract each other with strong Coulomb forces. What are the properties of salts? Get a salt. Yes. What are the properties of a salt? No. Hard, brittle solids, high melting and boiling points, and it will conduct in the melted or dissolved state. All right. This has been hammered into you since grade 8. All right. Now, people, in the next section of this chapter, we are going to have a look at how to make a salt. Now, 90% of the reactions that we use to make salts are the reactions with acids. So, for example, an acid plus a metal, an acid plus a base, an acid, plus a carbonate. All right. Now we can add other salts together as well, and it can react and form something new. We'll have a look at that right in the end. But just very basically, all of them, the product is a salt. It doesn't matter which reaction we use, because with this one, we get hydrogen. It doesn't contaminate the solution because it bubbles off. It's a gas. If it's a base, well, it forms water as a byproduct, but this reaction is occurring in a watery medium, so the water is not a problem either. And lastly, we will get a water and carbon dioxide, which also shouldn't be a problem because carbon dioxide is a gas and it is bubbled off. Okay. Carbon dioxide is slightly soluble in water, so it could possibly react and form a carbonate. So in general, we will ignore that happening, all right? And you will just assume the gas has been bubbled off. Now, there are different methods of making salts because the procedure that you use is different. The first method is we are going to take an acid plus a base. Now, the acids are all dissolved in water. Are you with me? They're all aqueous. The base that we work with can either be soluble or insoluble. Now, why do we differentiate that? Well, if you have your container with your acid and you add base to it, how are you going to know when the acid and the base have neutralized each other? Because I don't want to have acid left, because then if I start evaporating off the water, I'm not going to have a pure salt. There's going to be some acid left. Or if I've added too much base, base is also a salt. Okay, I don't specifically need universal, but I need an indicator. But if my base is soluble, I am going to need an indicator to tell me when neutralization has occurred. Can you understand that? All right. If the base that I've added is insoluble, I'm standing there with a spoon and I'm adding this powder into the acid, and it reacts with the acid. I warm the acid, I stir it, I allow it to react. Would it matter if I added too much of the insoluble base? I can filter it out, couldn't I? So when we have a base that is insoluble, we don't need an indicator. We add excess, we stir it, we heat it up, we give it enough time to react, and then we filter off the excess. And what are we left with? The salt and water. All right. I'm going to go and have a look at specific examples. If I want to make sodium chloride, what acid would I need? Yes, hydrochloric acid. I'm going to need HCl. Okay. What base am I going to need? Sodium oxide or sodium hydroxide? Let's just take take the sodium hydroxide. Doesn't matter. But what will I also need? Because sodium hydroxide is a solution. I am going to need an indicator. So I will go and I will measure out, let's say, I will go and measure out a specific volume of a specific concentration of my acid. All right? And then to that acid, I will go and add the base. I will do it carefully, because into the acid I go and add indicator, and then I add the base. So I will run in the base, stir it around, run in the base, stir it around, and you will find that at a certain point it's as if it's going to start changing color there where you run the base into the acid. Okay? At that point you have to work very carefully. If you know what you're doing, you can control it with a drop. so that on one drop, your indicator switches color. Then you know what has happened. What reaction? Neutralization has occurred. Now, usually when they do it like this, there's one of two ways. We can measure out the acid into a beaker. We usually put the base into a burette, and we run it from the burette into the acid. Technically, you shouldn't add stuff to acid, you add acid to stuff. So it would be more correct to put the base in a beaker with the indicator and run the acid into it. But we work with dilute solutions, so it won't really matter on the level that we work with it. If you have one burette, then you will repeat the experiment because you will measure how much you've run out. So on the next one, you will use the same amount of base and you're running acid into it. You will measure when you get close to the value, you will add a drop by drop so that you can get it literally to swap with one drop. And the drop is 0.05 milliliter. Okay, so your level of accuracy can be quite high. Yeah? Yes. But that you only want between an acid and a base. Because that's the neutralization point. It doesn't matter. You will choose the correct indicator depending on what you are working with. Okay, and you will accept that when it switches color, neutralization has occurred because that's what we're interested. Then you are left with a salt. Whether the salt is acidic or not is not important. But you are left with a salt and, well, hydrogen gas or water or whatever. Yeah. No. Litmus changes exactly in the middle. So if your acid and your base are of more or less the same strength, you will use litmus. But if you have a very strong acid and a weak base, you will use, I think, methyl orange. Yeah, this is difficult to explain exactly. Neutralization implies the acid and the base have destroyed each other. And when we work on the pH scale, we take neutral to be 7. But now I'm busy with neutralization. I'm making a salt. But the salt that I make can sometimes be acidic or basic. Yes, yes. Okay, with the acids and the base that you work with. Yes. No, you don't need a universal. You don't need a specific pH. You need an indication of when the acid and the base have destroyed each other. So, and that would be on the switch over. All right. So, people, you will go and add acid and base. When your indicator changes color, you know neutralization has occurred, and you will be left with sodium chloride and water. Now, we want sodium chloride. So, what would the next step be? I would heat it up so that we can evaporate some of the water. All right. Now, you don't normally boil it till it's dry because sometimes there are impurities in the water, in the solution, just a little bit of impurities. So what you're going to do is you evaporate off some of the water. So you heat it gently. You get a saturated solution. Okay, because you've heated off some of the water. And then you leave it to cool. And the moment it cools down, crystals start forming. And those crystals that would form in the cooled liquid would be pure salt. You can throw off the rest of the liquid, and then we say we wash and dry the crystals. You just rinse a little bit of distilled water over the surface of the crystals. If there are impurities, it'll wash it away. And then you would have a pure salt. Sodium chloride. That one. Yes. 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 You can do it like that, yes. Okay. We will go and make salts. And, well, you can drink the salt water if you like. The crystals, you can go and add it to your food as well when we're finished with it eventually, yes. Okay. So, people, that is the one way of making a salt. Let's say I'm still using an acid and a base, but now the base that I add is copper oxide. And this copper oxide is insoluble. So, I will, no, I don't want to make copper oxide, sorry. I want to make copper sulfate. Okay, I want to make copper sulfate. What acid must I use? Sulfuric acid. So I would need H2SO4, and I'm going to add to, really, the base is copper oxide, but I want to make copper sulfate, and over here I made sodium chloride. Okay, the base that I would add would be sodium oxide or sodium. All right. Doesn't matter. It's not going to, it won't matter. Whatever is available and what is the cheapest. Yeah, okay. What? Yeah, they'll be very similar. Yes, okay. Usually, the base that is not water soluble is in the oxide form. Can be a hydroxide. It's actually not, no, it's actually nonsense. It can be both. It just differs from one metal to another. Okay, now, people, when you want to make copper sulfate, but we are using an insoluble base. So I will go and add, oh goodness me, I want a different color. I will go and add my copper oxide. Now, copper oxide is a black powder. All right, it's insoluble. You added 2 sulfuric acid. What does sulfuric acid look like? It's a colorless liquid. Okay. Now, I go and add copper oxide to it. Now, when sulfuric acid reacts with copper oxide, my salt is going to be copper sulfate plus I'm going to get water. All right. What is the color of copper sulfate? Seriously? Blue. Why? What's the test for water? White copper sulfate turns blue. All right. So we're going to make the hydrated copper sulfate. Now, this stuff is soluble. It's going to be dissolved. That's why the solution turns blue. But what am I also going to have in that container? Excess. Excess of that. So once my reaction is run to completion, all the acid has reacted. I've got excess of that, and I've got that stuff in it, and water. How do I get rid of the water? I can evaporate it off, but before I evaporate off the water, what must I do? I must filter. Can you see I don't need an indicator? Because when I add the insoluble salt, it reacts and it forms a soluble salt. But the stuff that doesn't react couldn't react because all the acid has been used up. And I can filter off the insoluble part. And then I will be left with these two. How will I make copper sulfate? Gently heat to evaporate water to get a saturated solution. Allow it to cool and crystallize. And we will get the copper sulfate. No, you must have excess copper oxide because all the acid must react. Yes, the rule is, no, the rule is on the soluble salt, we have an indicator to tell us when neutralization has occurred. When we work with the insoluble one, you need to add excess to ensure that all the acid has reacted. Otherwise, you are going to be left with some acid in this mixture. No, you can't. Okay, then your salt will be contaminated. So you must add excess. You heat it, you stir it, you allow it to react, you give it enough time. And then you filter off excess. Say again? No. No. Okay. You could, but very often the salt that is produced is blue, so it's going to mask the color of the indicator. Yeah. Okay. So this then is one way of making salts. The first one, using a soluble base. The second one, using an insoluble base. So if you go and have a look in your textbooks, there at the bottom of page 82, figure 5.6, sequence for preparing soluble salts like zinc sulfate. Okay? And please write in there, what have they not got there? Yes, no, we are making, from an insoluble base. They must, in other words, write in there, they've got it written below the second beaker, the excess solid will not dissolve. All right. Then, where's the one with the soluble salt on the next page? Okay, then on page 84, there they have the burette and they run the acid into the base. What do we need over there? An indicator, write it in, because you're going to forget it and they don't mention it. You need an indicator to show you when neutralization has occurred. The third method of making a salt is we are going to use two soluble reagents, and the salt that we are going to make is insoluble. Remember, with both of the previous examples, this salt that I've made over here, that one, is water soluble. The difference that I had was over here my base was soluble and here my base was insoluble. But this salt that we made was soluble. Now, this salt that we are going to make is now insoluble. So, what are we going to do? We are going to use a soluble plus a soluble, and we are going to make an insoluble salt plus whatever. Now, the example that we are going to do is, hang on. Okay, now, the example that your syllabus prescribes is to make lead iodide. Okay? Now, which salts are soluble? I need something containing lead, and I need something containing iodine. Okay, so lead nitrate. All nitrates are soluble. Plus, well, all iodides are soluble except silver, lead, and mercury, so potassium iodide. They are liquids. They are both colorless liquids. All right? No, we don't have an acid and a base. This is just using two soluble salts to make an insoluble one.
So it's two soluble salts?
Yes. All right. So we will add lead nitrate to potassium iodide. This is colorless. This is colorless. Sometimes very light yellow, but for all sakes and purposes, colorless. Lead iodide is yellow. It's a bright yellow. Okay? And it's insoluble. What else are we going to get? This stuff. Soluble or insoluble? Soluble. It's soluble. All nitrates are soluble. So how do I get rid of that? Yes, I will filter. Yes, we want the residue. And what we do is we wash the residue just with distilled water. So if there are any contaminants on the surface, then it washes off. Okay. Are you with me? 3 methods of making salts. For your syllabus, this is what we do. All right. The first one, a soluble base. The second one, an insoluble base. And the third one, using 2 soluble liquids. and it gives you an insoluble salt. All right. In your textbooks, that one is making an insoluble salt, bottom of page 84. And any insoluble salt can be prepared in this way. The salt is made up out of 2 ions, that ion and that ion. All right. The anion and the cation. To prepare an insoluble salt, all that is needed is a solution of a soluble compound that contains the cation and the soluble of the compound that contains the negative ion. Are you with me? All right. A soluble compound. Then they are added together, and you will get the precipitate together with the nitrate. It's in the watery solution. You can filter off the insoluble salt. You can wash it and dry it. That, I think, is the end of today.
There's something else going on.
Have you ever seen someone die in front of you?
Once.
He's a school teacher. He's a local family man.
That's what he wants everybody to believe.
Death isn't going away. It's getting closer.
Follow Detective Harry Ambrose as he uncovers the most disturbing case of his career in the 3rd installment of The Sinner. If you're itching for more serial entertainment, then tune into Bull and discover the science behind winning a case. Or delve into the twisted world of Isono, a brand new African telenovela. And live large with Don Cheadle as he builds a Wall Street empire in Black Monday. Only the best series right here on DS.
Prevention is important. Help prevent the spread of illness and keep yourself and others well. Hand washing is one of the most effective ways of preventing the spread of germs. Wash your hands regularly with soap and hot water, scrubbing your hands thoroughly for at least 20 seconds. Hand sanitizers can be used but are not recommended as a substitute for hand washing. Use sanitizers in addition to hand washing or in a situation where soap and water are not available. To avoid spreading germs, limit sharing of personal items such as utensils, cups, and dishes. Your skin acts as a barrier to germs, but your eyes, nose, and mouth are more vulnerable. Wash your hands thoroughly before touching your face, eating, or drinking. Avoid physical contact with others, including handshakes, fist bumps, high fives, hugs, and kisses. Social distancing is deliberately increasing the physical space between people to avoid spreading germs. While regulations may vary by country or area, the best guideline for social distancing is to maintain a distance of 6 feet from others. Germs can travel through the air from one person to another. If you sneeze or cough, do so into a tissue or the inside of your elbow to prevent the spread of germs. Avoid contact with ill individuals and insist they isolate themselves until they have recovered and are symptom-free. Clean and sanitize frequently touched common surfaces and high-traffic areas in your home and workplace several times a day. Share these guidelines with others and help prevent the spread of illness and maintain a healthy environment.